All right, hello and welcome to Space Traps number 103. My name is Nick Schragle. I am a graduate student at the University of Arizona and Steward Observatory. For those of you who are new to Space Drafts, who are first-time attendees, welcome. Space Drafts is a Space Drafts is part of the Astronomy on Tap network, which is a network of public talks in bars just like this one all around the world, where professionals come and share astronomy with the public. Now, it's not normally this cramped. Usually we have our events outside, but we thought we'd give you a little respite from the cold this time. Typically how our show works, we have two 25-minute talks with a 20-minute intermission in between. This time, unfortunately, we do not have our typical astronomy in the news, but we have two great talks for you today.
There's news.
Oh, we do have news. We do have news. My bad. We do have news.
Danny almost got away with it.
Almost got away with it. So, with our talks, we have trivia, and that is your chance to win a little bit of Space Drafts merch. So each of our speakers will have a multiple choice question for someone in the audience to answer correctly and win a little piece of merch over at our merch table. Speaking of merch, there is merch there for you to purchase. If I say merch one more time, I'm going to lose my mind. But merch over there, we only take cash, unfortunately. So come back next time if you don't have your cash on you. Grab some Space Drafts merch. We also just finished AAS, the meeting of the American Astronomical Society. So over there we have some freebies for you from that. Finally, we are planted right next to a railroad track. So it is tradition here in Tucson at Space Drafts for when we have a train come through and interrupt our speaker, all of us raise our glasses and toast the train with a hearty choo-choo. With that, I would like to introduce our first speaker today. They are going to be talking about radio telescopes that are actually larger than they appear. Please give a warm welcome to Steward Observatory postdoc, Dr. Jackie Champagne.
Okay, hi everybody. I'm taking off my news hat. I'm not a news anchor today. Danny did not get away with it though. He will be back. All right, I'm a postdoc at Steward, and today I'm going to be talking to you about radio interferometry, and soon you will understand why this is the best joke of all time. Whose baseline is it anyway? So basically, every time I get up here and talk about news, I talk about the James Webb Space Telescope. I have to yell. Ah. Hello? Okay, that sounds good. No?
Yep. It was, and then it wasn't. I swear Yes? No. Yes.
Hello? Wait, amazing! Maybe? Yes.
Yes.
Okay. Anyway.
Just use your inside Jersey voice.
Okay. She's so nice. Hello? I can yell. Yes? Uh-huh. Okay, well, I am from the great state of New Jersey, so I can use my outside voice if necessary. Okay, so basically every time I'm up here, I talk about the James Webb Space Telescope. It's the sexiest telescope we ever built. It's in space. We love it. We're always talking about first galaxies that ever formed. But we need some love for the longer wavelengths, the radio telescope. And I'm going to talk to you about how we make networks of radio telescopes work together. Warnings and disclaimers. This is not a talk about astrophotography. If you came here and you're like, I love space. I love pictures of space. I can't wait to see more pictures of nebulae and galaxies. Not going to happen here. Not in the radio universe. But this talk is going to convince you. Why? No? Okay. Interferometry is magic. Okay, so we do radio astronomy from the ground. There's a reason that we do that. Basically, we can't put one in space. But luckily, we can use the Earth's atmosphere to our advantage. So here is the wavelengths of light going from short wavelengths to long wavelengths. And all of these brown things are areas where we cannot see through the atmosphere. We have pesky things like ozone, oh no, and water vapor in the optical and infrared bands. But all of this radio in the megahertz to terahertz range is free for the taking. And so we can see light completely uninterrupted in the radio. And if we want to do optical and infrared, we either need really fancy telescopes on the ground that do all kinds of optical things that I don't understand at all, or we put them in space. Okay, so why do I care about radio wavelengths? Who cares what's going on in these long wavelengths? Well, a lot. We have the Milky Way galaxy, you live there, and it's very bright in something called synchrotron emission. It's visible at exactly 408 megahertz. Did you know that? And that is the background image here. Black holes and quasars, so they're like throwing out light at every single wavelength you can imagine. And so we can see these actively accreting black holes in radio. Supernovae, after they explode, they also emit radio waves. Pulsars, which are cool stars that have these giant magnetic fields that are kind of beamed right at you, and they spin, and then you can get them to radio. Also aliens. Maybe you've heard of the movie Contact. People love to ask me, do you listen to your radio waves? Do you listen to the aliens? And Carl Sagan did that to us radio astronomers. He really made you think. However, if aliens were going to contact us, the radio bands would be the most sensible way to do it. Okay, so let's design a radio telescope. The most popular telescope type today is a parabolic reflector with a Cassegrain focus, and that is what you are seeing here. They're big dishes. But that was not the original prototype. We have many different ways of capturing radio waves. So this is a horn antenna, and this is a wire antenna, and those led to very important discoveries. These are like Nobel Prize winning discoveries, things like the cosmic microwave background and the 21 centimeter line of neutral hydrogen. So we have been looking at radio waves basically since like the 1940s-ish, and it originated in what state? New Jersey. Okay, here's your first trivia question. I have thrown so much information at you. Now let's use our intuition. Where is the best place to put a radio telescope? Is it the Atacama Desert in Chile, Mauna Kea in Hawaii, Antarctica, all the above, or only AIM?
All of the above.
Hello? So true, it is all of the above. Okay, so the reason for that. You want a location with very little water vapor. We talked about water vapor being really pesky in the atmosphere. And so going to really high altitude above most of the atmosphere is great. Also a place where it never rains. Excellent. And so here is what that looks like. Here's a map of the world, not a map of the universe, just the world. And you can see that in these zones of very low water vapor, we have Hawaii. So Mauna Kea is an amazing place to do astronomy, and the Andes Mountains in the Atacama Desert. But the South Pole Telescope needs some love too. Technically, Antarctica is a big old desert, so we put one there too. It's just that you can see less of the sky and the poles, so that's kind of but what are you going to do? It's a great place to do radio astronomy. Okay. Forgive me, it's so hot up here. Okay, so now we know that radio waves are out there. But what if I wanted to look at a picture of a radio image? Well, I need something that is going to give me spatial resolution. So basically, a really good camera that's going to let me figure out what the heck I'm looking at, that has a shape. And so your spatial resolution, or the smallest thing that you can see and actually make out what it is proportional to the wavelength you're looking at and the size of your telescope. So here's a comparison here. The Keck telescope in Hawaii is really big. It's 10 meters across. That is, a world-class telescope to be put on the ground. And that operates in optical and infrared. We have Hubble, the Hubble Space Telescope, which is 2.4 meters across, but that operated at shorter wavelengths, so that makes sense. And then we stuck James Webb in space at 6.5 meters. Why not 10 meters? Ask the engineers. You can't put something that big in space. But then here's Spitzer, which is an infrared telescope, and so you're like, well, why isn't that big? Well, Spitzer saw blobs. Spitzer was revolutionary, by the way, but Spitzer saw blobs. So you might imagine that really long wavelengths with radio. How are we going to build something really, really big? Here's the Green Bank Telescope next to the Washington Monument and the Statue of Liberty. So basically, we have this problem of needing to build telescopes that are impossibly large. It's like those nightmares where you're running and you're never getting away from the thing. Like you just have this infinitely large need for a big telescope. So we tried that. Here's the 300-foot telescope in Greenback, West Virginia, and in November 1988, it collapsed. So, we'll run out for Greenback. Okay, so building something that's really, really big, and you can also like steer it and move it and point it at different spots in the sky, not an easy engineering task. So let's cheat. Now we get to the magic of interferometry. We're going to interfere waves. So I'm going to take one telescope and another telescope, and I'm going to separate them by sun space. We're going to call that a baseline. Here's my astronomical source. It's emitting radio waves in all directions. So technically, I can put a telescope here and a telescope here. It's seeing two different waves. Light travels at a finite speed, so I know exactly how long it takes to get from one baseline to the next. So this is called the UV plane, not the ultraviolet plane. Don't get it twisted. This is radio. The UV plane is where we put our telescopes. And so we're going to correlate the two signals. Here's a bunch of complicated electronics, blah, blah, blah. Waves turn into electrons, batteries, yada, yada, yada. And then we correlate them, and you get an image. Okay, here's one more trivia question. Which French guy lends his name to the mathematical function, allowing us to transform time-correlated signals into an image? Is it Cassegrain, Fourier, Lagrange, Dirichlet, or Fermat? Yay! You guys are so engineering. So it is Joseph Fourier. So let's see what happens next. You guys want to do some math? Let's do that. All right, so here is the Fourier transform. Let's go through every term in this equation. Okay. LOL. Visibilities. Okay, so we're going from the UV plane where we've collected all of our time-correlated signals. You're just going to take a 2D Fourier transform. Simple. Is the brightness function of the sky. So you have two things that you're measuring. You have the brightness, so just how bright the source is, and you have a phase, which is the position of the waves that you're measuring. And so this is what it looks like if you were to have a uniform disk on the sky and take the 2D Fourier transform. You're going to have this ring-like thing. So now we have an idea of what a typical astronomical source is going to look like after we correlate these images. And so the beauty of the Fourier transform, if you happen to be familiar with this mathematical concept, is that you can take pretty much anything and make it a series of sines and cosines. But forget about that. We're just going to build an infinitely large number of telescopes. Forget about the whole big telescope thing. We're just going to make a bajillion of them. And the more baselines you have, or the more pairs of telescopes that you have, the closer and closer you get to the actual astronomical source. So you're just taking the average of all of these things. This is just two telescopes. It's obviously like completely unusable. What are they looking at? But the more baselines I have, finally, I get the brightness of a single source. People who are not radio astronomers, like look at this and they're terrified, and well, that's not a galaxy and that's scary. But I got taught this first. So everyone was like, oh, James Webb Space Telescope, look at these beautiful nebulae. And I'm like, what's the Fourier transform? So, on to the astral plane. Let's use more baselines. Okay, so we're getting lots and lots of telescopes. And the other problem is that you need to be collecting light. You can't just have like tiny little telescopes all over the place. You also need to have a dish that's actually collecting things. Guess what you can do? You can just wait for a really long time. The Earth rotates, which means things in the sky move. Technically, that's another baseline. So here's two antennas. This is now in the image plane. You can see there is no galaxy. But now we add more and more antennas. And soon the Earth will start rotating. Oh my God, it's rotating. And you can see how this image is getting better and better and better. Until finally, that little point of light is a real astronomical source. Okay, so I said that you can't just have an infinitely large number of point telescopes. They need to also be actually collecting light. So we call this sampling the UV plane. We want all these spots on Earth to be taken up with something that's collecting light. So the short baselines, where the telescopes are really close together, are really good for picking up all of the light coming from your astronomical source. So here's this guy. It might be David. I don't know. Here's David. And we have some short baselines. And you can see the general shape of David. You can tell where he's bright and where he's dark. But you can't really make out anything else about him. So now we're going to add in long baselines. The further apart your telescopes are, the more we're mimicking that whole like diameter relationship. And so now, with the long baselines, we pick up all of these really fine details about data, but we're missing a lot of that brightness information. So we call that resolving out the flux, but really it just means you're missing stuff. But when you get both, when you have an amazing network of telescopes, now you can finally see data. But we don't have to do this. I don't know when. Okay, so the ultimate image, you might be wondering, okay.
Choo choo!
Maybe I have not yet impressed you. Maybe you're like, okay, she's a little cuckoo. I'm not really seeing anything fascinating about the universe. What about a black hole? Will that impress you? Here is a black hole. The event horizon of a black hole, the rim around, you get spaghettified and get closer, is only about a light year across. And so, 25 years ago, we started doing simulations of what it would take to see the rim around a black hole. And it wasn't looking good, because we need millions of an arc-second spatial resolution, which is, a really fun. I was going to try to come up with an analogy. It's like a bajillion of a million. So anyway, 15 years ago, I had to update this talk. It didn't used to say 15. I wrote this when I was a grad student. 15 years ago, we could produce the resolution of 1 arc-second. Now we need to get a million times better than that. And so this was our best effort of looking at a black hole. But then we invented very long baseline interferometry, where now our baseline is the whole Earth. And so we took this network of telescopes in Hawaii, Chile, Europe, Japan, and we started using them together. And so watch as these baselines start to come together, we populate this UV plane, and now our spatial resolution is getting better and better. Very soon, we're going to finally have a ring, and that ring is the event horizon around the telescope. So we call it the event horizon telescope, obviously. What else are you going to call it? And so, is that the end of my video? Okay, the good one's on the next slide, don't worry. Okay, whose baseline is it anyway? Thank you. Now you get it. Okay, well, it's supposed to put the Steinfeld baseline, but you know what that sounds like. So. Alright, so just how good is the Event Horizon Telescope image? Okay, it's 52 millionths of an arc-second. So this is the sum diameter here. This is how good this image is. You're saying it's still blurry. I could take a better one with my iPhone. Wrong. This is the same as if you were standing here on Earth and you can look at the moon and see a donut on the moon and figure out that there is a hole in that donut. The other thing that the press release said, and I love this one too, if you were to stand in New York City and look at a newspaper at a cafe table in Paris, you could read the newspaper. That's how good this is. It's crazy. So, what is in the future? Super duper long baseline interferometry. Let's put a telescope on the moon, okay? Hear me out. Putting a telescope on the moon or an array element in low Earth orbit would not only improve the resolution of PHT, but also fill in that UV coverage so much faster. So let me show you what I mean. We're trying to get a point of light from every part of this space. And as this thing is orbiting and you're using the baseline for every single telescope, now you have both the fine details and all of the light. So we can actually see this black hole in amazing detail. But don't give me Elon Musk any ideas, because I don't think it's going to be okay. Okay, so I will close with some shameless, advertisements of my own work. Here's ALMA, the Atacama Large Millimeter Array. It's my favorite telescope. Oh, I'm wearing short sleeves. Here you go. So that's all. Okay, and so here's a black hole. You can't quite see the event horizon, but the cool thing about this black hole is that it existed 1 billion years after the Big Bang. Here we are 13 billion years later. But we're chilling, and we can see all this light from the black hole. This is short baselines, so we have a lot of light. But then this other guy followed it up with longer baselines, and so now you can see more detail. Maybe there's another galaxy over here. Maybe this is like all kind of, disk and stuff like that. Actually, it's a rotating disk. Here's another thing that I did. I spent 4 years of my PhD thinking about this. Let us ponder. Okay, so I spent all this time talking about images, looking at pictures. Another thing you can do is break up all that light and actually find the emission signatures of individual atoms and molecules. Here's carbon monoxide coming from galaxies that are a couple billion years after the Big Bang. Every single one of these yellow things is a different galaxy full of carbon monoxide, which allows us to figure out how many stars that a galaxy can form. And so now, we're not only resolving the detail of a single galaxy, but we're seeing these streams of gas all in between them, which is so cool. Okay, so finally, we are revealing the magic. I am awed by this all the time. For radio interferometers to work, all of these things have to be true. That dishes can focus plane waves. That light behaves both like a wave and a particle, and it travels at a finite speed, and we can take advantage of that. The fact that we were able to invent electronics to correlate these voltage signals only, 150 years after Maxwell wrote down the equations. And also Fourier was a genius. We have these signals that you just type in, do some math, and then you get an image, and it works perfectly every time. And then we can see the entire radio universe. There's so much out there emitting radio waves, and we just need to build 1,000 more. And so that's the end. Thank you so much for listening. I hope you love radio astronomy now too. Thank you. You have burning questions? Well, I'll have to yell again.
It's kind of something's happening.
Hello? Oh, yeah. Yes.
When you're looking at galaxies far, far away, like billions of light years, you have to correct the redshift of the radio waves?
Yes. Yes. So when you're looking at galaxies billions of light years away, you have to correct the radio waves for how far away they are, or the redshift. And yes. So this carbon monoxide emits at 115 gigahertz, but this is at redshift 2. So this is instead, I'm going to have to go to a longer wavelength array because it's redshifted. So this is the very large array in New Mexico. And this happens to emit at 33 gigahertz, which is your Wi-Fi. So you can't have anything fun at the very large array. Yes.
What radio telescopes do better than optical telescopes?
Did you say why are radio telescopes better?
What do they do better?
What do they do better?
Oh, what do they do better? Oh, everything. Sorry.
Pretty pictures?
Sorry to the Space Telescope Science Institute, who I have applied for to fund my work. I love optical and infrared astronomy. There's just totally different features. So when you see starlight, that is very bright in the visible, and the infrared and the UV, so stars kind of take up everything. But the radio telescopes are able to see things that other telescopes simply will never be able to find, like magnetic fields and these very kind of low frequency undulations of the universe. I'll leave it at that. Thank you.
Okay. Thank you, Jackie. So we're going to take 20 minutes. Go and have a refresh. Go and get a refresh for your drink. We have our merch table over here for the people who answer their questions. We'll get you a little freebie over at the merch table. Yeah, don't forget to tip your bartender, and we'll see you back here in 20. That will be at about 8. That will be 8:20. See you then.
Yeah.
Alrighty, welcome back to the back half of Spacecrafts. Before we get to our second talk, we are going to take a look at what the recent goings-on in the nighttime sky with astronomy in the news. So, that will be presented by Steward Postdoc, Dr. Danny Cassidy. Danny, take it away.
Thank you so much. Hello, everyone. It's nice to be back doing the news. You're stuck with just me today. All of the jokes were front-loaded in Jackie's talk, so I apologize ahead of time. So to get started, we're going to begin with a farewell, and we're saying goodbye to I think what is arguably one of the most important, not just modern astronomical missions, but probably one of the most important astronomical missions of all time, and this is the Gaia mission. So what is Gaia? So Gaia is a European Space Agency spacecraft that had a telescope that observed the entire night sky regularly for just over a decade. And it was able to very precisely measure the positions and brightnesses of billions of objects, both mostly in the Milky Way, but also outside of the Milky Way, to really enhance our understanding of really almost all fields of astronomy. So why are we saying goodbye to this wonderful, revolutionary mission? Well, it's it's all because it ran out of fuel. So last week, they officially ceased science operations for Gaia because it ran out of fuel, so it could not position itself quite well enough. And so they are shutting the mission down. No more science data is being taken, and it will soon be kind of shuttered off into a different orbit to waste away from anything that might bother other spacecraft. So what was the main goal of this mission? So like I said, it was able to measure the positions and brightnesses of objects all over the sky, with the main goal of doing this for billions of stars in the Milky Way to make a three-dimensional map of our local universe. And so it did this, like I said, by kind of just staring all across the sky and able to measure where a star was in the sky to such high precision, it would be the same kind of measurement precision that if you were trying to see the width of a human hair from about 650 miles away. So I did like a little search of what city is 650 miles away from Tucson? There aren't really any big ones. So it's like trying to see a human hair in Lubbock. Why you would ever want to do that, I don't know. But that's what it is, so okay. And so by measuring where the stars were so precisely for over a decade, they could see how its position was changing to get both how far away the star was and how it's moving through the galaxy. And so by doing this, you're able to reconstruct a three-dimensional map of our local universe, which tells us so much about how all of these stars and our galaxy have formed. And so this mission really touched on all areas of astronomy. This is since 2016 when it released its first data release. I remember I was a first semester grad student very excitedly downloading the Gaia DR1 catalog. It's been a long time since then. And it's collected about a petabyte worth of data. So that's like you have, a few thousand phones just lying around with all of these data, which, considering all the data is literally just numbers of where stars are, it's a lot of measurements. And so this has helped us understand things all the way from locally, how groups of stars nearby have formed together and evolved, providing ages for planet-hosting stars. It's found a plethora of objects nearby, from nearby asteroids to exoplanets to black holes. By mapping the Milky Way, we've learned more about the Milky Way shape and structure, and it's even created catalogs of quasars, distant quasars, to help study large-scale structure of the universe. So this really is a great loss, but even though the spacecraft is shutting down, things are not done for Gaia. Like I said, there's all of that data, which much of it has still not yet been processed. There are 2 more data releases planned, one for 2026, which probably means 2027, and then one by the end of the decade, which probably means 2035. But it will be very exciting once astronomers can get their hand on all of this data, because we have barely scratched the surface, I think, of the Gaia data to date. And so there's even more coming in the decades to come. So this will not be the last time you hear about Gaia data, but it will sadly be the last time you hear about Gaia, the spacecraft. So moving on, normally I talk about the solar system and stars and planets, and here I am now talking about James Webb and galaxies, so good luck to me and to all of you. So kind of, this story is a continuation of a cycle that seems to have been prevalent with James Webb science, where there's excitement at new data, confusion over the results, kind of freaking out about physics being broken, and then everyone being like, oh, okay. Whew, we figured it out, everything is totally fine, physics is not broken. So what happened? So since Webb launched, it has found a lot of these so-called little red dots, which you can see a collection of there. You can see it's quite well named. They look exactly the same to me, but I guess they're not. And so there was a big question of, what are these? And so they are actually galaxies that are from the very early universe. And so, okay, they could know what it is, but there was the question of how do they exist, how do they form? And this was initially kind of concerning, because if these galaxies are all made up of stars, as galaxies normally are, they're a bit too massive for having formed that early in the universe's life. And so there was a lot of questions like, okay, well, how did this happen? Is the universe older than we think it is? Is physics broken? Like, what's going on? Well, that's not good. But this is not as much of an issue as some seem to have made it. There was a new study that was just talked about at a press conference, I believe, at the meeting of the American Astronomical Society last week by the early release science team Sears, combining a whole bunch of public data from the James Webb Space Telescope that says that these little red dots are not just galaxies, but they are AGNs. They're supermassive black holes that are accreting a lot of material. And so a lot of their brightness is not just from stars in the galaxy, but it's from the accretion disk around the black hole eating all of this material. And so that means there's less stars than they thought from the initial models, which means they're less massive, so they're not breaking physics, which is wonderful. And not only that, there's all of these now early universe black holes that can be used to understand better how other black holes have formed and evolved, including our own supermassive black hole at the center of the Milky Way. So this does not solve everything. There's still a lot of degeneracies in the models. They need to take more detailed data to find out exactly what's going on. Are these really accreting black holes? They think so, but more data is needed. So thankfully, we can wrap up that cycle of the James Webb, that version of the James Webb cycle until they take more data, find something broken, and then freak out all over again. And so just one last story, just to kind of end a bit on a maybe serious note, a bit closer to home for all of us. If you haven't been following the news, I'm sure most of you are aware of this. There have been truly devastating wildfires in the LA area, and this includes affecting many astronomers that are employed, not just astronomers, but staff employed at NASA's Jet Propulsion Laboratory, Caltech, and other institutes in Pasadena. And so I just wanted to, mention this. It's been really devastating. Hundreds, at least, employees and astronomers at Caltech and JPL have been affected by this, not just being displaced, but many have lost their homes. And so I just wanted to kind of say, if it's in your means, I think donations would be very greatly appreciated by all these people. I have a QR code here for an astronomer-led GoFundMe. Also, you could just Google, Caltech disaster relief or whatnot, or of course any other disaster relief. Thoughts go out to obviously not just astronomers that have been affected by this, but many other people who live in the LA area, the firefighters that have been working so hard to contain these fires. So I just wanted to kind of end on this real life, no. Astronomy is done by astronomers, and so it really matters that the people doing the science are, and all the people helping us do the science are okay. So thanks, and that's another Astronomy in the News.
Alrighty, yes, please give this fund if you can. There are quite a few people who are suffering due to those fires in LA. So yes, if you have the means, please do give. To bring us to our last talk of today, we have PhD candidate from Steward Observatory, Meredith Stone, who's going to be showing us how some galaxies in our universe are further away than they actually appear. So please give a warm welcome to Meredith.
Hi everyone, thank you for sticking around. I had a line planned about how I appreciated you sticking around to freeze, but maybe not so much. Today we are here for, I don't have enough hands to do this, a birthday celebration. Because, for my money, 100 years ago, almost exactly, thank you Hayden for getting me on the party hat. I tried to go to Party City and buy one party hat. They don't sell single party hats. So I've got like 12 if you want a party hat. For my money, almost exactly 100 years ago, the field of extragalactic astronomy was founded. And you might say, that's oddly recent, or that's oddly specific. And indeed, it is. In fact, the field of extragalactic astronomy is younger than 4 of these 5 inventions/people. 4 of these 5 nouns. And so I would like to pose you the question, oh my God, Hayden, this is the old version of my slides.
It is?
Yes.
Oh, I'm so sorry. I can probably fix
It's
that.
okay, I have another trivia question.
Do you? Okay.
All is not lost. I was going to ask you which of these is younger than the field of extragalactic astronomy. Unfortunately, I seem to have given away the game. In fact, both America's sweetheart Betty White, artificial sweeteners, contact lenses, and modern paper clips were invented before we knew what galaxies were or that they lay outside the Milky Way. The only thing on this list that post-dates the field of extragalactic astronomy is clear Scotch tape. But you might think that's sort of a weird thing to say, because astronomy is one of the oldest fields of science. There are galaxies that are visible to the naked eye. Haven't people been observing galaxies since the dawn of time? And that is true. However, it's sort of true on a different level than something like, say, stellar astronomy, where all the way back to the classical era, people were making these very careful catalogs of stellar positions and brightnesses. I've not looked this up, this is purely based on vibes, but I think that it is probably true that from the evolution of modern humans up until the invention of the telescope in the early 17th century, humanity as a whole probably witnessed more visible naked eye supernovae than they did unique galaxies. Up until the early 17th century, depending on where you lived and the elevation that you lived and how much of your life you were willing to spend staring at the sky instead of sleeping, you could see up to 7 galaxies. It's not a lot. The most famous of which, of course, are the Andromeda Galaxy, visible from a lot of places around the world, and the Magellanic Clouds, visible from the southern hemisphere. But once the telescope was invented, it was realized that a lot more of these types of objects, like Andromeda, like the Magellanic Clouds, existed, and they were termed the spiral nebulae because they had these distinct spiral arm features. There were lots of these. They were very pretty. People drew them with varying, I don't know if you've ever seen a photo of the Pinwheel Galaxy, but with varying degrees of accuracy. And they were counted, and their positions were recorded. And once photography, and specifically astrophotography, were invented, they made fantastic targets for that. And so that brings us up to the early 20th century, where we have a lot of information about the spiral nebulae, but their nature and how they may differ from, say, other types of nebulae, other types of fuzzy non-star things in the sky, is highly unclear. So bringing us to the beginning of the 20th century, spiral nebulae are very much in vogue, sparked in part by a very interesting result spurred by spectroscopy, which has already come up once tonight, and which you've almost certainly heard of if you've been to more than one of these spacecrafts. So spectroscopy is when we take a source of light, the sun, a star, even a spiral nebula, pass its light through a prism, and we've all seen the album cover. We split its light into its constituent colors or wavelengths. Spectroscopy is super useful to astronomers for a wide variety of reasons, not the least of which is every chemical element in whatever is emitting the light imprints its unique fingerprint onto the spectrum that results. So for example, if we see a pattern of spectral lines that looks like this, we know the object contains nitrogen. A pattern like this, oxygen. A pattern like this, hydrogen. However, there is an additional complication because these lines may not appear where they canonically should be. This makes things a little more difficult, but it's also very useful to astronomers because the positions of these lines indicate the motion of the source. How does this work? We've got a source, it's emitting light, and that light is reaching our telescope on artist's impression of Earth. The normal spectrum looks like this. However, if the source is moving towards us, that spectrum, that light gets, this is the technical term, squished. Those peaks get pushed closer together, i.e. the wavelength decreases. All of the spectral lines therefore move to shorter wavelengths or become bluer. This is a blue shift. Conversely, if the object is moving away from us, that wavelength of light is stretched, the wavelength becomes longer, and all of those spectral lines move to longer wavelengths. They are redshifted. And the degree of this shift of the spectral lines depends on how fast the object is moving. So slow-moving object, small shift, fast-moving object, larger shift. And so we can use this is just the Doppler effect, same thing that affects the pitch of an ambulance siren or a car engine, to determine how quickly things are moving. Very useful information. And so, at the beginning of the 20th century, the technique of spectroscopy had advanced enough that we were able to start taking spectra of the spiral nebulae. And this work was was performed by one of the first of many excellent early 20th century names you will encounter in this presentation. Unfortunately, we're kind of starting with the best one. This is Vesto Slipher, and his life truly is a tale of tragedy because he was born with this name much too late to become a scheming vizier. He was also from Indiana, which didn't help, and much too early to be a Harry Potter villain, and so he had no choice but to turn to astronomy. So after he finished his undergrad education, he moved to Lowell Observatory, which at the time was still run by the, we'll say, irascible Percival Lowell, most famous for the discovery of canals on Mars, well, not Mars, on Mars, from an intelligent civilization. Also, if you know, you know, indirectly responsible for the founding of Steward Observatory. But so Slipher moved to Lowell Observatory to take spectra and study the motion and composition of the sun and planets. However, after about a decade, he switched to studying the motion and composition of the spiral nebulae, and he found something really interesting. So he was looking at two lines of sulfur because A, they're bright, and B, they're close together, and so it's easy to spot them because it's these two lines close to each other. You can see that in these spiral nebulae spectra here. And what he found, two things. One, almost all of the spiral nebulae he looked at were redshifted, i.e. moving away from Earth rather than towards it. Two, he noticed that the degree of this shift, how far the lines were away from where they were supposed to be, the spiral nebulae with a greater redshift looked smaller in the images, almost as if they were further away. Put a pin in that. He presented his results at a meeting of the American Astronomical Society in 1914. Apparently he got a standing ovation. And this table is from a couple years later with a larger sample of galaxies. So this is 25 galaxies. 4 of them are blue shifted, the remaining 21 are red shifted, and moving at extreme velocities up to more than 1,000 kilometers per second. For context, Earth moves around the sun at about 30 kilometers per second. 1,000 kilometers per second is like traveling from New York to LA in just under 4 seconds. It's very, very fast. And so this really strange result that differed between the spiral nebulae and the rest of the nebulae, no other type of nebulae were moving this quickly, really intensified the debate about the nature of the spiral nebulae. Were they small clusters of stars and gas and dust that lay within the Milky Way galaxy, or were they island universes? It's important to remember this is 1917, the same year that Einstein published his theory of general relativity. At the time, the entire universe was the Milky Way. It was not understood that there was anything beyond the Milky Way galaxy. To call a galaxy and a universe were synonymous. But these spiral nebulae were weird. And when I say the debate intensified, I do mean that literally. At a different meeting of the American Astronomical Society, this one in 1920, there was a structured debate organized to present all of the evidence, all of the data that had been taken on the spiral nebulae, and say, what is the nature of these things? A couple more great 1920s names. On the one side, Harlow Shapley was arguing that the spiral nebulae were small structures lying within the Milky Way. Heber Curtis, on the other hand, was arguing that they were independent, distant island universes. Shapley's argument that they lay within the Milky Way went something like this. For one, the distances required were so extreme. So at the time, it was known that the Milky Way was a few tens of thousands of light years across. He argued if the Andromeda Nebula were the size of the Milky Way, to appear as small as it does in the sky, it would have to be millions of light years away. Ha ha ha, isn't that ridiculous? On top of that, he pointed to some observations that had been done recently of the Pinwheel Nebula, where someone had observed the nebula multiple times over years and had observed it rotate slightly. And he argued that if the spiral nebulae were as far away as Curtis was claiming they were, for that rotation to be discernible, they'd have to be moving so fast they'd tear themselves apart. On the other hand, Curtis argued that the spiral nebulae, unlike any other type of nebulae, post too many novae. Novae are a type of stellar explosion on the surface of a white dwarf star, and they occur at a much greater rate in the spiral nebulae than in any other region of the Milky Way. To have a lot of stellar explosions, you need a lot of stars, so Curtis argued that the spiral nebulae must have a greater number of stars than other typical star clusters and nebulae. He also pointed out the spiral nebulae have dust lanes. Dust lanes are the dark parts here, where it's not an absence of stars, it's where starlight is blocked by dust. It was understood in 1920 that this was the phenomenon. And the reason it was understood is because it was observed in the Milky Way. There are regions of the Milky Way where it looks like there are fewer stars, but in fact the stars are just obscured by dust. So he said this is probably an analogous structure. And finally, he pointed to Slipher's results. The recession velocities are incredibly large. It's not beyond the realm of possibility that some of these are greater than the escape velocity of the Milky Way. So even if they're part of the galaxy right now, they're not going to be. And so, of course, only one of these arguments, only one of these sides can be correct. However, it was all based on legitimate astronomical observations, except for one. So, for a trivia question that will not give away the answer immediately, one of these main pieces of evidence presented in the debate is based on faulty observations. Which one is it? So the first one is, if the spiral nebulae are the size of the Milky Way, they'd have to be millions of light years away. The second one is, we've seen the spiral nebulae rotating on human timescales. Third one is the hosting more novae than any other part of the Milky Way. Fourth one is the dust lanes thing. Fifth one is the recession velocities, Slipher's results. Anyone? B. That is correct. So all of the rest of these points are, confusingly with the red color coding, true. Those observations hold up. Galaxies do not rotate on scales that we can see. Something about those observations went wrong. But the rest of this was true. Funny enough, Shapley was awarded the winner of the debate. So, ha ha, funny. But the sort of elephant in the room this entire time has been, it would be very easy to settle this great debate if we simply measured the distance to one of the spiral nebulae. Unfortunately, in astronomy, measuring distance is much more difficult than measuring, say, velocity, which you can do with the spectrum. Because the methods that we use on Earth to measure distance don't really work in space. So this is my old slides, so I'm going to skip this because I cut it out because this talk was too long. Stars. We'd like to know the distances to stars. Unfortunately, all stars, basically regardless of their distances, look the same. And this is because stars are so small relative to how far away they are that we cannot resolve them. We cannot make out any details of their surfaces, and we can't measure how big they are. So stars are out. We can't use their sizes to determine how far away they are. And other things that we can resolve, like for example planetary nebulae, tend to come in a wide range of sizes. So this is a picture of the Ring Nebula and the Saturn Nebula, and they're scaled to the actual sizes that they appear on the sky. And if these two planetary nebulae were the same size, you'd be able to say, okay, the Saturn Nebula must be much further away because it appears much smaller. But that is not the case. We can't use size, it's not useful. What astronomers use a lot more often is apparent brightness. The way this works, it's again something that your eyes can do. If you know how bright something should be, and you measure how bright it appears to be, you can determine how far away it is. If you know something is bright, but it appears faint, it must be far away. And the relationship between these quantities, luminosity, intrinsically how bright something is, how bright it appears, the flux, and the distance, have a very simple mathematical relationship. Problem is, it's actually pretty hard to find types of sources where we, a priori, know intrinsically how bright it is, just by looking at it. It's easy to measure how bright something appears. It's harder to know how bright it truly is, and we need both of these ingredients if we want to find the distance. A type of source where we know intrinsically how bright it is just by looking at it is called a standard candle. And again, we take this known luminosity of our standard candle, and we combine it with our flux measurement to get a distance. So rewinding back to the beginning of the 20th century, everyone was wanting to find standard candles. Distances to some nearby stars were known through a method called geometric parallax, which is essentially measuring how much a star shifts in the sky over the course of a year, but that only works for very nearby stars. Stuff that's further away, you need a standard candle. So everyone was looking for these. The person who would find one is one of the most underappreciated people in this presentation, Henrietta Leavitt. So Leavitt was part of the famous, if you're an astronomer, group of Harvard computers, who were women who worked at Harvard Observatory in the late 19th and early 20th centuries, and their job was to measure brightnesses of stars from photographic plates that were taken as part of Harvard's survey of the sky. And so Leavitt, who is in this picture, came to Harvard in the 1890s, worked on the photographic plates for a few years, left for a couple years, and then came back in 1903. And in 1903, when she returned, she was given a specific project having to do with this poster on the wall behind her. This is a plot of the brightness of a certain star over time. You can see it raises and falls and rises and falls and rises and falls in this nice periodic motion. This is a variable star, a star whose brightness changes with time. When she returned to Harvard, she was assigned to study variable stars in the Small Magellanic Cloud, which we now know is a small galaxy that orbits the Milky Way. She became interested in a particular type of variable star called a Cepheid variable. Cepheids are supergiant stars, so they're very bright, and they vary with this nice periodic motion. Cepheid variables, because the first one was found in the constellation Cepheus, the star Delta Cephei. So Leavitt was looking at this data of the Small Magellanic Cloud, and she noticed that the bright Cepheids tended to vary in brightness slowly, whereas the faint Cepheids varied very quickly. And she made the breakthrough that this must be a real effect that she's seeing, because all the stars in the Small Magellanic Cloud are in the same distance. So, normally if you just look at a patch of stars, you have the problem of, okay, is this faint thing that I'm seeing actually faint, or is it just far away, bright and far away? But if you're looking at a bunch of stars that are all the same distance, then you can make plots of things like apparent brightness versus period of oscillation, how long a star takes to go from bright to faint to bright again. And you won't have that sort of contamination, that confusion from looking at things that are different distances. And she realized that her hunch was correct. So this is how long the star takes to oscillate, this is how bright it is, and she saw that indeed brighter stars take longer to oscillate. And the final breakthrough, there were some Cepheids that were close enough to have distances measured via parallax. And so, by using that as a calibration, she could convert this relationship between period and apparent brightness to a relationship between period and luminosity. Why does that matter? Well, period is something we can observe just by looking at a star. So if we have the period and we can get the luminosity from it, and we can measure the flux through those same images, we have everything we need to get the distance to any Cepheid anywhere in the sky just by looking at how long it takes to oscillate and how bright it appears. So now, all anyone had to do is find a Cepheid variable in a spiral nebula. The person who would do that is one of the least underappreciated people in this presentation, Edwin Hubble. You might have heard of him. So Hubble, after he finished his PhD, he moved to Mount Wilson Observatory, which is in California, and used this telescope to look for Cepheids in spiral nebulae. This was a tough process. He'd have a couple of photographic plates in front of him like this, taken a couple of weeks apart, and he would scan back and forth between them, probably ruining his eyes, but training his brain to notice the tiny differences between the two, something that wasn't present and then suddenly appeared. Unfortunately, if you were here last month, you heard about the wide variety of things in the sky besides variable stars that can appear and disappear and reappear. And Hubble had to worry about novae, which we talked about earlier, those stellar explosions on the surfaces of white dwarfs. Luckily, it is possible to distinguish a nova from a variable star. Novae explode and then they don't go off again for a while. Years, decades, sometimes never. A variable star, a Cepheid variable, is always oscillating. Bright, faint, bright, faint, bright, faint. And so he had his two photographic plates he was comparing, and then off to the side he had a third photographic plate taken even earlier. And if he saw something that was present, not present, he could go back to the third photographic plate, and if it reappeared there, then it was a variable star. If it wasn't in there, it was probably a nova. So, this brings us to early 1924. Hubble was looking over some data that he'd taken in the previous fall. This is from October 6, 1923. It looks like a 1913. Looking back and forth between these photographic plates. He sees something in the disk of Andromeda. Present, not present, not present. It's a nova. He marks it with an N for nova. He finds something further out in the disk. Present, not present, not present. Nova. He marks it. And he sees a third thing even further out in the halo of Andromeda. Present, not present, not present. No, there's nothing there. So he marks it with an N. But something makes him go back and look at that little patch of sky again in that third photographic plate. It doesn't really look like there's anything there, but maybe. And so he winds up going and getting a fourth photographic plate out of storage. Present, not present, not present, present. And so he puts down his black pen, he picks up a red pen, he crosses out that N that he just wrote, and in big, red, capital letters, exclamation point, he writes variable. Hubble had just discovered a Cepheid variable in the Andromeda Nebula. And over the next several months, he found more of these, both in the Andromeda Nebula and the Triangulum Nebula, and a few months later, he leaked his own results to the New York Times. On November 22nd, 1924, he converted those periods to luminosities, those luminosities to distances, and he had found that the Andromeda Galaxy and the Triangulum Galaxy lay at a distance of around 1 million light years. This was wrong. They're actually like 2 million light years away. But this was correct enough to realize that they were well outside the few tens of thousands of light years limits of the Milky Way galaxy. However, we know that a very charismatic press conference does not necessarily equal a robust scientific result, cold fusion. And so for my money, the science of extragalactic astronomy was not founded on November 22nd, 1924. It was founded on January 1st, 1925, when Hubble's results were presented, interestingly, not by him. He was not there. Someone else presented them for him at a meeting of the American Astronomical Society. 100 years ago, almost exactly. Plus or minus 20 days, which for an astronomer is a fantastic error bar. We will take that at any error. This was not remotely the end of Hubble's career, and it's really interesting how after this date, questions that we still are trying to answer in the field of extragalactic astronomy were immediately posed. So for example, Hubble found more Cepheids in more spiral nebulae and published a paper the next year talking about the wide variety in shapes and sizes that he had found in what were now called the extragalactic nebulae. And about a decade later, in this textbook that he wrote, he put forth the first attempt at an explanation of how this diversity came to be. And this is still something that is a central focus of extragalactic astronomy today. What causes the wide variety of galaxies we see? He also confirmed Slipher's results from now more than a decade earlier. Slipher had noticed that the galaxies that were moving faster tended to appear smaller in the images, and he thought maybe this means they're further away. But without robust distances, he couldn't be sure. Hubble combined his distances with Slipher's velocities and realized that there is in fact a linear relationship between these quantities. Galaxies that were further away moved faster. It's a linear relation. He calculated the slope, which is now called the Hubble constant. And that's great. He did that. We can check it off the list, and no one ever had to worry about the Hubble constant ever again. Now, it's been 100 years of studying galaxies, knowing what they are and where they lie. and the field has exploded, not only in number of people studying it, but also scale. We're studying the same galaxies that Hubble studied, that the first telescopes looked at, that prehistoric people from the evolution of humanity have looked at, and we're also studying galaxies at the frontier of the visible universe. It's been 100 years, a lot of questions have been answered, but we're still trying to figure out what causes the diversity of galaxies that we see. How did they all get here, and how did we get here in this particular part of this particular galaxy at this particular time? 100 years of answers, but many, 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 many more questions still to come. Speaking of questions, I will happily take yours. Thank you so much. Speechless. However,
So, why did people think, why did people used to think that, spiral nebulae, they rotate or spin on human timescales?
yeah, so the question was, why did people think that the observations of the Pinwheel Galaxy, where someone noticed it spinning, what happened there? I'm not totally sure. I think it was probably just a problem with the astrometry or the calibration, where he was comparing to like some sort of background star, and also it was the 1920s and it was all photographic plates. So there's a lot of things that could have gone wrong there. But yeah, galaxies do not rotate on human timescales. That was an error in measurement. Oh.
So when do people start calling them galaxies instead of?
That's a good question. So the question was, when do people start calling them galaxies instead of extragalactic nebulae? And there's an interesting historical context here, which is for a long time, I said galaxy and universe were simultaneous. For a long time, galaxy was the Milky Way. It's the same etymology, the lax in there is milk. And so it took a little bit, I think, for people to really internalize that we have the capital G galaxy, the Milky Way, but these are equivalent little g galaxies. So I'm not sure exactly when that shift happened, but yeah, it took a while because the term in vogue was extragalactic nebulae for a while first. People didn't want to go with that nebula word.
So back then, were people not able to see individual stars in galaxies in the photographic waves, and was that why they were not able to?
Yeah, so the question was, were people not able to see individual stars in these galaxies? So a galaxy has a lot of stars. We look at this photo of Andromeda and we see that there's a lot of stars there. And so people must have realized, right, that there must be a lot of stars in these things. And yeah, it's exactly right. With the dust, with the resolution of photographic plates, it just wasn't possible to resolve the crowding the way that we can today. This is why all of the Cepheids and Novae that Hubble found were on the outskirts of the Andromeda galaxy, not near the center. Because near the center there was just way too much crowding. He never would have been able to distinguish a Cepheid from the 10 stars it was blended with.
How many light years away can
Yeah, so this is so the question is, how many light years away can we see Cepheid variables and use that as a distance indicator? I don't know the number off the top of my head, but it has increased greatly with time, partly for this crowding reason. As we've gotten bigger telescopes with better resolution, we're able to separate the Cepheids from the stars around them and spot them. I would say, I think of everything in terms of megaparsecs. Comanche is showing 10 figures, 10 megaparsecs. 10 megaparsecs are about 30 million light years. So yeah, a lot further than we now know that Andromeda is about 2 million light years away, not 1 million like Hubble thought. Factor of 2, good enough. All right, thank you so much, everyone. I really appreciate it.
Alrighty. And with that, we will bring spacecraft number 103 to a close. Thank you all very much for attending today. Sorry we had to cram you in here, but hopefully you enjoyed not being out in the cold. Our next show will be on February 18th. So once again, thank you so much. If you want a little bit of merch, we still have some merch over the table. Yeah, and with that, thank you all for coming. We'll see you back here, same time, same place, February 18th.